I'm Carola Schönlieb, I'm Professor of Applied Mathematics. Welcome to my exp. Image processing is the manipulation, or let's say a group of techniques that manipulates images. Could be manipulating images to enhance content in these images, like removing noise or de-blurring it. Or could be processing or manipulating images to quantify things in images, like segmenting objects in these images, estimating shapes of these objects or color. This is what image processing does, and doing this, developing methods that can do this in an automated fashion, without or with only minimal human intervention. We develop mathematical methods alongside theory for these methods for various different imaging, image processing, image analysis tasks, ranging from image reconstruction from indirect measurements like tomographic measurements in medical imaging, for instance, in CT or MRI, where what you measure is not an image directly, but there is some mathematical work transformation involved that you need to go through before you can look at an image that is interpretable. All the way to quantification based on imaging data, so segmentation, so isolating objects in images, tracking them, and so on and so forth. And usually the development of these methodologies, which are very generic in themselves, is linked to quite specific real-world applications where a lot of the interdisciplinary work comes in that we do in fields like biology, medicine, material sciences, cultural heritage, all the way to conservation and even forensics. Partial differential equations are equations of a function that depends on more than one variable. So 2, 3, and so on, higher dimensional, so functions living in 2, 3 higher dimensions, and that describe changes of this function and relate changes of this function to each other. So one really good example, or easy example, is the diffusion equation, which describes the change, the evolution of a quantity that is represented by this function over time, and equals it to the flux of the gradient of this function. So the flux of the spatial derivative of this function. And so this could, for instance, describe very nicely if you have a cup with hot tea and you pour milk into this tea, you can see the milk diffusing into the tea. This, to a certain extent, you can think of is based on diffusion. This is describing diffusion of the milk over time, and you can describe this by the heat equation. Another example is heat tells you something about distribution of heat in a room. It can tell you how, if I have in a room like this, if I have two sources of heat, like my two radiators here, how does the heat from these sources distribute into the room? And so this can be nicely used to instead of thinking about heat, thinking about intensity function as like color or gray values in an image, and diffusing color and gray values in this image, which, for instance, you could use to smooth an image and get rid of things like noise in this image, which again you can think of as a component that is very rough in this image, in this color intensity function that you want to smooth out with this diffusion process. If you want to denoise an image, it means what you want to do is you want to subtract noise from the image to uncover the clean image underneath. That's the simple task, let's say. The issues that you have usually with this is that noise that is added to an image is random. You don't know, you sometimes know what the distribution of this noise is, which can help you developing methods to subtract the noise. But it's not that you know what the intensity of this noise is in every pixel. If you would, you can just subtract it and then you have your clean image. So it's a random thing that has been done to your image. So now the goal is to decompose this random component. Usually, if you look at the rainbow, you can imagine that this is a very highly oscillatory component. Intensities are changing randomly from one pixel to the next. You want to subtract this random component from the clean, structured, smooth, to some extent, image underneath. So in imaging language, in image processing language, it would mean if I use diffusion to denoise the image, I denoise it because I diffuse all the intensities spatially, which in particular will kill this highly oscillatory component. Of course, it will also kill some of the very sharp features that I have. So it's blurring the image everywhere. But this is why, you know, mathematical methods and why image processing exists as a field, to develop differential equations that go beyond the heat equation, but that can weigh diffusion, let's say, by the amount of content that there is underneath. So you diffuse less when you have sharp features that you would like to preserve, and you diffuse more in regions where your intensity, your color function is kind of constant or nearly constant. And as such, you can get a crisp image that doesn't have noise. We can take actually again the diffusion equation as an example. In the video that you see, this is called harmonic inpainting. So what we do there is we have an image and we have some objects in this image that we want to remove. What you want to do is you want to take out an object like a snowball, for instance, and you would like to replace it by something that it makes visual sense, right? So the main goal of image inpainting is, which is restoration of digital images, is to replace the snowball by something that is visually plausible by what you see from the rest of the image, or from, let's say, your experience of how what is potentially behind the snowball. We use the intensity values on the boundary of the snowball, on the edges of the snowball, and then we diffuse these into the inpainting domain, which is defined by the snowball. Now, taking magnetic resonance imaging as an example, here the goal is usually to image faster, right? For anyone who has been in a magnetic resonance imaging machine before knows that it is not very nice to be in there. And so doing this faster makes it much more acceptable for the patients. It makes also the processes in the hospital much more efficient, and also it might allow you also to look more at things that dynamically happen in the human body, right? So you need a certain amount of measurements for each image snapshot in time, but if you want to look at things dynamically, you have less time per time snapshot, if that makes sense. This is just one example, and in this whole medical imaging field, where mathematics can help to optimize the trade-off between how much effort, how much money, how much time you put into measurements. Yeah? So in computer tomography and X-ray imaging, this could also relate to radiation, how much you radiate the patient. The less you radiate, the more noise you usually have in these measurements. So to optimize this trade-off between this and the quality of the image. And so, for instance, in a collaboration that we had with a former postdoc of mine and colleagues at Addenbrooke's Hospital, we developed mathematical methods that could help speed up the the process of magnetic resonance imaging acquisition by an order of magnitude, right? So instead of being there for tens of minutes, for like half an hour or more, you could actually reduce this to just a couple of minutes without losing information content. The beauty of mathematical imaging is, on the one hand, that mathematics is an abstract language, right? It's a way to abstract problems, right? If I develop a segmentation algorithm for segmenting cells in biological images like time-lapse microscopy images, for instance. The same algorithm with a bit of adjustment we can use to segment stars in astronomical images. This is the beauty of this, that a lot of these methods translate from one field to the next in terms of application domain. And then it's a matter of choosing. There are lots of examples where images appear. They appear in healthcare, they appear in cultural heritage, they appear in environmental monitoring, in material sciences. A lot of research and also everyday life of how we operate nowadays is dependent on automated interpretation of imaging data, loads of digital imaging data.